Hi, in this video we are doing the LTspice simulation of the emitter follower as an output stage. So first we connect the V1 voltage source as our output. So assuming our output has been amplified to have a peak-to-peak of 2 volts and the frequency we don't expect to have it changed. Okay, so we are not using any bias here. I'm going to put a resistor. Obviously we need one, else our output voltage will be tied to the ground. So the resistor R1, call it RE with there's a value, and that is going to be, let me give it 100 ohms. Okay, so that's RE. Now we run and see what happens. 10 milliseconds. Okay, so our output is not taken from the collector. The collector is tied to the VCC, so we expect to see 5 volts. Our input, as we expected, a 2 volt sinusoidal, and our output. So why are we getting these clippings? This was explained in the last video. When the output input signal is not enough to bias the so when the input signal is not enough to bias the transistor, the output will stay off until the input signal is somewhere here enough to bias the transistor. That is when the output begins to follow the input. That's why we call it emitter follower. Now when it gets to this point, when the output is still not enough to bias the transistor, then the output will still be 0. During this cycle, the negative cycle, the input is giving out negative base emitter voltage, meaning there can't be any output. So clearly you can see that there is no bias. So what I can do is I can use bias, which means that will be constant voltage, which I can get that by means of any of what we know. But for simplicity, I'm just going to use a voltage source so that we don't have to do any calculation by picking resistance, but we can still do the divider. Okay, but this shouldn't be too difficult, but let me just use a voltage source. So if I have 5 volts here, I could use voltage to divide and get appropriate voltage. So what I want to do is I want this device to be always forward active or forward bias. So I'll start by putting 0.7 there, and we'll see why 0.7 might not be enough. So I wouldn't do the resistor because I'll be changing the bias voltage. So 0.7 here. So this becomes my bias voltage, and there's output signal from the first stage, which I'm not showing, which has been amplified. So this is the story here. I have a microphone giving me 10 millivolts peak to peak, and has gone through whether my differential amplifier or single stage, whatever it is. So let's assume a differential amplifier which has been connected or converted to a single ended by using the current mirrors, as we did in some 2 videos ago. Now we want to connect that to a speaker. If you connected that directly to a speaker, we would get no output. So what we are going to do now is I have my okay, so let's first look at the bias. Alright, so this time around, by biasing it 0.7, it means that the input signal no longer starts from 0. The input signal starts from which one is the input, which one is the output. Okay, let me recheck that. So this is the input. The input should be node 2 together with the bias. Okay, so you should take node 3 and the output being node 4. Okay, so you're looking at node 3 and node 4. So node 3 is a new input with bias. So instead of starting from 0, now you're starting from 0.7, as you can see. So right at the beginning, the signal the output can follow because there is bias. But even with this, when it gets to the negative, as soon as we push beyond the 0.6, then the output begins to go off. But I could correct this if I raise the bias. So let me see how much more I need. So if I raise the bias by extra 1.2, so to be on the safer side, I'm going to give a bias of 2.7 volts. That's actually what I need. So a bias of 2.7 volts, which means that corresponding current is going to flow through the device throughout. So let me run this, and the current corresponding to the 2.7 volt, that looks small to me. I was expecting more. 19.5 milliamperes. Okay, let me change this to 4.3 and see. Okay, yeah, all right, so I forgot something. All right, so I'm not getting as high current as I would because of the emitter resistor. So as the current increases, the emitter voltage would also raise to oppose the current. So there's some sort of increase in output impedance, which is also a good thing. Imagine there were no resistor here. And I run. Now with the resistor, we saw the current that we got. And now the resistor, we are getting IC current of 3.8. Okay, I even expected more than that, but I think that's all that this current can supply. Let me give 30 volts here and see. Okay, 4.8. So due to supply limitation, all right, that makes a lot of sense. You are not going to get the 10 raised to the power 57 we would get if we use our calculator to punch in the bias current. So I'm going back to my 5 volts and taking this to 2.7. So we are bringing back our emitter. Okay, then we run and we check our input. So our raw input and our, okay, so this is our raw input and this is the input with the bias, and we have our emitter follower, and always the difference will be 1 VBE because part of the voltage coming in is dropped across the VBE before it follows the emitter. That's why we call it emitter follower. So you've seen the major drawback. We need huge biasing voltage. That means huge current should be flowing through this always, which is not good. So especially as the voltage rises, we need more bias voltage, more current, and that is not good. So there's a better way of doing that, and that's called the pull push stage. So in the pull push stage, I will just introduce us to that here. the pull, push, pull, pull, push, any of them that sounds nicer, but I'm sure it's one of them. Can't really remember. Okay, so maybe by the next video I'll really check it out. So what we do is we connect the output this way. So we have our output signal coming in, AC. So this is our emitter resistor. So this is NPN. Then the output is taken from here. Then this time we put a PMP here. Then we can connect our output. So we can connect our load, which is our speaker, and see. Okay, so this time around, when the signal goes in 2 cycles or lower cycle, so in the upper cycle, the base emitter junction would be on, while during that cycle this transistor would be off. So you have an output, and during the lower cycle, the negative cycle, this transistor will not be conducting, and this transistor rather would be conducting. So take our time and go much into this push-pull output stage and see how it's better than the emitter degeneration, the emitter follower. It also has its own drawbacks. So this forms a class B, and we look at how it's improved by forming what we call a class AB. So the drawback we can also look at is, while this guy is going up, the same issue of this needs to be biased, so the output will still sort of go like that, because at this stage, because there's no biasing, the transistor would still be off. Okay, so we'll look at that into details in the next video. Until then, see you. Bye.